If I asked you, how long will it take to empty this pool, you'd say it wasn't much of a question. A pipe that takes 5 days to empty the swimming pool will empty the pool in, how about 5 days? If I asked you how long it will take pipe 2 to empty the pool, it's just as easy, 7 days. Duh. But as soon as we wonder what might happen if we used both pipes working together and ask how many days it will take to do the job, we have a very different kind of situation. It's called a rate of work problem. It looks like it might be hard, but it isn't. In fact, I can show you 3 things that are very easy to do with this problem. First, we can do it wrong very easily. Second, we can estimate the right answer very easily. And third, we can find the right answer very easily. First, a wrong answer? That's very easy. Pipe 1 takes 5 days. Pipe 2 takes 7 days. Both pipes? 12 days? Wrong. We can't add them together because it's going to take less than 7 days and even less than 5 days because we have 2 pipes working instead of 1. Here's another easy way to do it wrong. Average it out and pick the midpoint between 5 and 7. So we say it will take 6 days to do the job. Wrong. Since one of our pipes does it in 5 days, 2 pipes certainly won't take longer than that. The answer will have to be less than 5 days. So how can we get closer to the right answer? If we consider some alternatives, we can estimate the right answer very easily. All we have to do is imagine that both pipes are the same. First we try 2 pipe 1s and then 2 pipe 2s. If they're both like pipe 1, each can do the job in 5 days. So together, they do it in half that time, 2.5 days. If they're both like pipe 2, each can do the job in 7 days. So together, they can do it in 3.5. But we actually have 2 different pipes, one slow pipe and one fast. So the right answer is going to be more than 2.5 days, because pipe 2 is slower than pipe 1, but it's going to be less than 3.5 days because pipe 1 is faster than pipe 2. Our answer then is going to be more than 2.5 and less than 3.5. But don't go thinking it's exactly between the two, namely 3 days. That's just another one of those easy ways to do it wrong. But there's an easy way to do it right. All we have to do is shift our point of view and change the units we're talking about. Instead of days to empty one pool, which emphasizes the pool, let's talk about how many pools we can empty in one day, which emphasizes days. Only when we know how much emptying each pipe can do in the same period of time can we figure out how much work they can do together. If pipe 1 drains 1 pool in 5 days, then it must drain 1/5 of the pool each day. What about pipe 2? It drains the pool in 7 days. So in 1 unit of time, 1 day, it drains 1/7 of the pool. Now we have a common measure of the work each pipe can do. We have found the daily rate at which each pipe is draining the pool. With that information, we can combine the work done by both pipes and find our answer. The pool is going to be empty in 2 11/12 days. We'll see how to do that in a minute. That matches our original estimate. It's between 2.5 and 3.5 days. And it's not exactly 3 days, but it's pretty close, as we predicted. Here's a good way to think about the whole problem and solution all at once. We translate the work of each pipe into pools per day, a rate, following the arrows left to right. We then combine the two following the vertical arrow. Finally, we translate the total back to the left to find our answer. We work in a circular pattern with 3 steps. 2 steps translating information when we follow the arrows from left to right, or right to left, and 1 step on the right where we just add fractions together. This is a pattern we can use to solve all sorts of problems about rates of work. Once you've got it, you'll find the algebra becomes quite simple. We've already determined how much of the pool each pipe drains in 1 day. We want to know how much of the pool will be drained by both pipes together in a day. How do we find that? Simply by adding together 1/5 and 1/7. The amount pipe 1 will empty combined with the amount pipe 2 will empty. We find the lowest common denominator, 35. 1/5 becomes 7/35. 1/7 becomes 5/35. We can now combine 5/35 and 7/35, and we find that both pipes working together drain 12/35 of the pool in one day. But that wasn't the question. What we really want to find is how long does it take to drain the whole pool in days? We deal with that by realizing we now have a simple proportion right out of basic math, and it's solved in 2 steps. First, divide both parts by 12. This tells us that draining 12/35 of the pool in one day is the same as draining 1/35 of the pool in 1/12 day. For the next step, we multiply both parts by 35. And now we see that draining 1/35 of the pool in 1/12 day is the same as draining 35/35 of the pool, the whole pool, in 35/12 days. Notice that our answer has just taken the fraction we started with, 12/35, and turned it upside down. Here's another rate problem to try on your own. You can use the same pattern we used in our first example to handle it. Just take it one step at a time. Pause the program, and when you have your answer, click play again, and we will work through the steps together. Let's analyze what this problem tells us as we look for an approximate answer. Bill does it in 6 hours. Mary does it in 4. If Mary was as slow as Bill, together they would take 3 hours. If Bill was as fast as Mary, together they would take 2 hours. If Bill and Mary work at the same rate, the answer is easy. But they don't. All we can say is that the answer should lie between the 2 speeds, somewhere between 2 and 3 hours. To find the answer, we need to be able to combine the work Bill does to the work that Mary does. We must translate their speeds into some unit that we can add together. To do that, I use the same kind of statement I used in the pool example. Remember? We did that to shift our point of view from one pool to one day. Here I'm going to shift my point of view from one kitchen to 1 hour. And suddenly we have a way to solve our problem. In 1 hour, Bill paints 1/6 of the kitchen, and Mary paints 1/4. We can add 1/6 and 1/4 by using the lowest common denominator, 12. This tells us that together they paint 5/12 of the kitchen in 1 hour. But we want to know how long it takes to paint 12/12 of the kitchen, the whole thing. If you already understand why it works, you can just use our retranslation method and turn the fraction over. 5/12 becomes 12/5, which is the same as 2 2/5 hours. But if you don't see why we turn that fraction over, go ahead and do the math. Once again, it's a proportion, and again we solve it in 2 steps. They do 5/12 of the work in 1 hour. Divide both parts by 5, and we find they do 1/12 of the work in 1/5 hour. Then the crucial step. Multiply both parts by 12 to find out how long it takes to do 12/12 of the work, the whole job. And again, the answer is 12/5. Another way to approach the process of translation, combining, and then translation back is by an equation that represents the word problem we're trying to solve. It's harder to follow, and it's not so good in complicated problems, but it is the math behind the pattern we've followed. We use the unknown x to represent the number of hours it will take for both Mary and Bill to paint the room together. To solve it, we need to remember all the material in the module about equations with fractions. You may need to review. We start by multiplying both sides by our lowest common denominator. Then we cancel to remove the fractions. We can now divide to get the same answer we had before, 2 2/5 hours. Good. Our 2 approaches agree. Now let's do one last rate of work problem together. You're rafting down a river with a friend when suddenly the raft springs a leak. You jump to the rescue with a cup. You don't bother to awaken your companion. He's a heavy sleeper. After 2 hours of bailing, you're sure you can finish the job in a total of 5 hours without any help. Your friend finally awakens from all that splashing and senses that something's wrong. She grabs her cowboy hat and starts bailing as well. And in 2 more hours, you're finished. Now here's the question. What if you had been asleep and your friend emptied the whole raft by herself? How long would it have taken her? Is there a way to find out? How in the world do we begin? Let's start writing down the fact. You can begin to see this is a puzzle like our earlier examples, except that it's a little bit more complex, and we have a different piece missing. Let's approach this problem the way we did before, and see how much of the raft you actually emptied in 2 hours, and how much work was left to be done, because that tells us how much of the raft you emptied together after she woke up, 3/5 of the raft. Then we shift our units from 2 hours to 1 hour. We find that in 1 hour you empty 3/10 of the raft together. Now we're ready to find out how fast your friend works. Remember, we already know that alone you can empty 1/5 in an hour. Now we also know that you can empty 3/10 in 1 hour together. The question is, how much can your friend do in 1 hour by herself? The answer is, she empties the part of the 3/10 that you don't. Your 1/5 is the same as 2/10, so that leaves 1/10 for her. She can empty 1/10 of the raft per hour. Now, back to the question. You sleep, she works. How long does it take her to empty the whole raft without help? She will have to empty 1/10 of the raft 10 times, which will take 10 hours. That would be one big job. You can find more examples like this in your textbook to practice solving. Make sure you understand why we ask the question, what happened in what unit of time? Then you'll be ready to apply the same approach to other similar problems you may encounter.